Next, we will look at the Minimax algorithm. This algorithm is basically the implementation of the Minimax function that we studied earlier. Given that max starts playing first, what we would like to know is what decision should max make at every node. So if max is playing at node A, what action should max take, whether A1, A2, or A3? Similarly, when max reaches node C, min reaches node C, no matter what action min takes, what action should max take after that? So this is given by the implementation of the minimax function in the form of this minimax decision algorithm. The idea behind algorithm, once again, because this definition is recursive, the implementation would also be recursive. It takes a state as input and returns an action. What action is best for max at that time? It is basically argmax of all the actions. That is, for all the possible actions, give me the action that gives me the maximum value for the first player. So let's start tracing this algorithm at for this game tree shown here. So the algorithm starts by trying to calculate minimax decision at node A. So we will start by trying to calculate minimax decision at node A. Now, what we return is argmax of all the possible actions and applying this min value function at those nodes. So here at this node, what we return is maximum of all the possible actions. Now, when we return the action that corresponds to that node, but for simplicity, we will say it's maximum of all the min values. So we will say min value at node B. Similarly, the next possible action is min value at node C, and the next possible action is min value at node D. So at this node, what we will return is the maximum of either of these three. That means before this function can return anything, we need to calculate each of these values individually. So let's try to calculate the min value at node B. So the function sort of forks out to calculate min value at node B. So we go to this function min value, taking node B as input because the result of being at this state A and taking the first action A1 will be node B. So this will return node B. So we call the min value function at node B. So sort of we forked out from here to call this function. We check if B is a terminal state or not. It's not, so that we skip this line. Then at this place V, we set V to infinite. So at this node, I maintain this variable V, which I currently set to infinite. Now at B, I look at all possible actions. For each actions in B, do the following. So for each action, let me start with the first action of B1. For each action, I set V to V equals minimum of the current V, which is infinite, and the max value at the resulting node. So here this will be max value at the resulting node, that is this node. Let's say this node is X. So the max value at this node. This node will be X because the result of being in node B and taking the action of B1 will give me the result node X. So I call the max value function at X. So that means now I'm going back to call another function max value with node X as input. So at X, we check if this is a terminal test, which it is, then we return its utility. So its utility is 3. So we return this as replacing the max value. So 3 is returned. So we replace this with 3. That means minimum of infinite and 3 is 3. So our V now becomes 3. So at this node, that is at the node min value, node B, that we were working at, we took the first action and updated v as 3. Now, since we were in this for loop, we finished calculating max value. We finished computing the minimum of current v and max value. Now we will continue taking more actions. So the next possible action is b2. The max value at node, let's say this is y, is 12. So this max value, entire thing comes to 12. So minimum of current v, that is 3, and 12 is still 3. So v remains at 3. We take the next action, so this will result in 8. So minimum of 3 and 8 will still be 3. So at the end, at node B, what we have is v equals 3, represented by this number here. And similarly, once we have completed mean value at node B with 3, we return this v where it was called. So mean value at node B will be 3. So here, since we're trying to calculate the maximum of all the possible actions, now this, we call this node B, this gets returned to min v, and this gets replaced with 3, associated with the action of A1. Similarly, to calculate min C, we go to this node and find out that the mean value is 2. We replace this with 2, and then similarly we go to calculate the mean value at node D. This returns us 2. So now, going back to the main function, what we are looking at is action A1 gives us 3, action A2 gives us 2, action A3 gives us 2 also. So the action that has maximum value is A1. So that means the decision that Max should make at this node, at the first node, is to go and take action A1. So this is how the Minimax algorithm works. Now let's look at the intuition behind these values. So the intuition is that what we would like to learn is, if the player Max is at node A, what are my chances of winning if I take various actions? If the player takes action A1 and then we go to node B, then min gets to play. In other words, at this time when we call the min value function, it is min's turn now. Now it's min's turn to play the game. So min will select the minimum value possible from all of these values, because the utility higher the better for Max and lower the better for min. So min will try to select the minimum possible values from all the possible actions. So obviously min will select 3. Similarly, at node C, since this entire level is min's turn, min will always try to select the minimum value after this node. So here min will select 2, and here min will select 2 as well. So here at this level, Max has no control over what he can select or what C can select. However, assuming that min always makes moves that are best for min, we can select the best action. So here, assuming that min has his turn here, min will always select 3, here min will select 2, and here min will select 2. So that means if it is Max's turn, it's safest for Max to choose this action so that he or she gets the maximum of the minimum possible actions that min is going to take. To come up with the minimax decision at a given node, an interesting question to ask is, do we need to compute all the minimax values, that is the v values that we had? Do we need to compute them at all the nodes in our game tree? The answer is no, and let's see how. Say we want to calculate the minimax value of the root node A in terms of x and y. Let's say we have utility values associated with our leaf nodes as shown here. And let's say we don't know the utility values associated with these two nodes, but then we know everything else. Let's see if our minimax decision, that is calculating the minimax value at node A, depends on these two utility values or not. So the maximum at node A will be maximum of minimum of 3, 12, and 8, because here min gets to play, and minimum of 2x and y, 2x and y, and minimum of 14, 5, and 2. So this is the minimax. This is from the minimax algorithm, minimax algorithm that we saw before. Because in bottom line, this is what the algorithm does: is try to calculate the maximum of minimum, and then after that maximum again and minimum recursively. So this evaluates to maximum of minimum of 3, 12, and 8 will be 3, and a minimum of 2x and y, we don't know how much it is, minimum of 2x and y, and then minimum of 14, 5, and 2 is 2, right? So what we would like to calculate here is the maximum of this expression. So let's look at the three terms that we have. We have 3, we have another term which is minimum of 2x and y, and we have another term 2. Since we are looking at the maximum values among these three, this 2 we can easily skip, because the maximum of 3 and 2 is obviously 2. Now we are left with two choices. We want to calculate the maximum of this number 3, or another number which is minimum between 2x and y. It is pretty clear that no matter what the values of x and y are, the minimum of this number will always be less than 2. That is because if x is a very large number, let's say 100, then the minimum of 2 and some large number will always be 2. If x is a small number, let's say 0, then the minimum of 2 and 0 will be 0, which is still less than 2. So we can guarantee that this expression will evaluate to something that's less than 2. Now that we know that, the maximum of 3 and another number, so maximum of 3 and another number that is less than 2 will always be 3. That's because since this number is less than 2, we have a guaranteed high number, then we can always pick 3. What's very interesting here is that the minimax decision, or the minimax value at root node, is not dependent on these values x and y, which we did not know. In other words, we can still calculate the minimax value at certain nodes without knowing the entire subtree below, without knowing the minimax values associated with many of the subtrees below. The immediate question is then, which nodes do I need to ignore? Which nodes can I ignore? In other words, we say which nodes to prune or ignore or not look at. Ignore. Now let us discuss the core idea behind pruning, that is, how to know which nodes to ignore. Consider a node n somewhere in a tree. So let's say this is your game tree, and we have node n at a certain place in the game tree. And let's say here's our player, here's our opponent, and here's our player, and here's our opponent. So at the beginning, the player, let's say, starts somewhere. At this point, player has a choice of going to node m. And then later on in the game tree, somewhere, the player also has a choice of going to this node n. The principle for pruning is that if this player has a better choice m, gold, somewhere in the path of the parent or any choices further up than the parent, and if the player has a choice of going to another node n, which is slightly worse than what we had a choice earlier, let's say this is brass, then the principle for pruning is that this player will never get to this node n. That is because if the player had a choice of going to a better node in the previous choices already, then the player, it makes no sense for the player to come all the way down to get to a node which is worse than what the player had already found. It is, however, possible that there may be better nodes towards this line, towards this side of the tree. However, at this point, somehow we know that because of the choices that opponent makes along the way, we know that if we go down this line, if we know enough about this node n, where we can say that, let's say this is less than 20 or less than 10, if we know that this node n or its subtree gives me something less than 10, and I already have, let's say, a big score like 30 at this node, then we can safely assume that our algorithm will never get to this node n. So that's the principle for pruning. Next, let's look at the alpha beta pruning algorithm. The alpha beta pruning algorithm is simply an extension of the Minimax decision algorithm. It's simply an extension of this algorithm. The key difference between the Minimax decision algorithm and the alpha beta search algorithm is that the Minimax decision algorithm looks at every possible node and calculates the minimax value at every node, that is min value and max value at every node, to compute the minimax decision at a given node. So minimax decision at a given node depends on all possible nodes or all children in the game tree. Whereas with this extension, what the alpha beta search does is it understands that some nodes may not be needed to calculate the minimax decision and intentionally ignores these nodes in the calculation, effectively reducing the calculations that need to be done. It can reduce the calculations to up to half, but the idea is to remove or ignore or prune the nodes in the game tree that are not needed to calculate the decision, to calculate the minimax value. So if you look at it, it's similar to the min-max decision. Here, instead of min-max decision, we have alpha beta search. We have the max value function, we have the max value function, we have the min value function, and we have the min value function. But all the trouble of making this minimax decision algorithm to alpha beta search is so that we can ignore the nodes that are not needed to calculate the minimax decision. So the core idea is to maintain two values at each node known as alpha and beta. So at each node of the game tree, we maintain alpha and beta at each node of the game tree. And the value of alpha represents the best node, that is highest value we have so far for the player max. So alpha represents the, in a way, utility or chances of winning for the player max at any node. And beta represents the best node with the lowest value along the path for min. So say for example, if we had, let's say at this node C, alpha equals 2 and beta equals 1, that means at this node the chances of max winning the game are high because this represents all the subtrees below, and we see that alpha which represents the chances of max winning is 2, and beta, which represents the chances of the second player min winning the game, is 1. So at any point at the end of the calculation, at any node, these values alpha and beta correspond to the best nodes for max and min respectively. So the core principle of the alpha beta search algorithm is to update the values of alpha and beta as we go along and prune the remaining branches at this node. Say for example, at this node D, let's say I find out alpha and beta, and let's say I find out that the values are such that after calculating this part of the node, I find that I'm going to possibly continue to decrease beta. But since at this level, let's say decreasing beta is not helpful for alpha, then there is no point in looking towards the remaining nodes. So at any node, since this algorithm works recursively, the values of alpha and beta get passed from this side to other sides as well because it works recursively. And as soon as we find out that a current node is known to be worse than the current values of alpha and beta for max and min respectively, we can quit. So say we processed this part of the tree and we obtained some value of alpha and beta for this root node A. Then after, at the time of taking the next action, if we see that whatever we try to come up here is worse than what we already have for alpha and beta, then we don't calculate this node.